Okay, we're continuing to talk about how to add waves together. And so now we want to talk about standing waves. And so if you recall in our previous lecture, we talked about that if you had a wall over here and then you had a string and you attach it to the wall, and then you're going to take the string and start to snap it up and down, it's going to start to generate a wave. And then that wave is going to go down the slinky or down the string. When it gets to the wall, it's going to be reflected and it's going to come back towards you. So if you are snapping it at just the right frequency, then what you can do is you can generate a standing wave. So let's say that this represents the wave that is traveling in this direction. So the wave that's going in the opposite direction could be represented with a dotted line, and it could look something like this. So notice that when one of the waves is going up, the other wave is going down. So this would be 1, 2, 3, 4 standing waves that are being generated. So it only occurs at a certain frequency, or a certain wavelength is going to correspond to a standing wave. But we're essentially adding two waves together. We're adding the original wave plus the reflected wave to make the standing wave. Well, we got some special words, nodes and antinodes. A node is going to be where you have minimum movement of the wave. So right here and then right here, notice the amplitude of the wave is at its minimum right there and right there, and you'd have another one here, you have another one here, and another one here. So these are all called nodes, and we're going to just say that it's an N for a node. An antinode is going to be where it has its maximum. So this one is at a maximum when it's way up here, so that this point is going to be an antinode. So we'll say A for antinode. Where else would you have one? So you're going to have another antinode here, and you'd have another one here, and finally you'd have another one right here. So notice it goes node, antinode, node, antinode. So they're always intermixed with each other that way. So I wonder if there isn't a relationship between the wavelength of the wave and nodes and antinodes. And it turns out that there is. So before I do that, let's just show you different kinds of nodes and antinodes, so that if you have a string and it's attached to a wall over here and you're flipping it upside down, the first kind of standing wave that you would have would be a really big one. So it's going to look like this. So that's one standing wave. And so that is the picture that is to the right and uppermost. Okay, then you could have two standing waves in there. So then that would be a case like this, where it goes across and then it goes up and then down like that. So then that would be two standing waves. And then this one here is four standing waves. But there's another way of doing it. What about if you had a straw? So if you had a straw, so that's going to be a tube, and it's going to be open on both ends. So this one here is where it's closed on both ends. And those are the different kinds of standing waves you can have. What about if it's open on both ends? So if it's open, then those are going to be antinodes, because that's where it's going to be at its maximum. And so you can see the different kinds of standing waves that could be set up in a straw And then what about in the middle? So the middle one would be, what about if you took the straw and you put your thumb over the end of one side of it, so that it's going to be closed on one side and then it's going to be open on the other side. So where it's closed, that's got to be a node. Where it's open, that has to be an antinode over there. And so again, notice all the different kinds of standing waves that can be generated. So it turns out that there's a relationship between the distance between nodes and the wavelength. So let's illustrate this over here. So actually, let's just do it for this one right here. So the wavelength lambda would be the distance from here. No, I'm sorry. So this is just going to be the distance L from here to here. So that's the distance from a node to a node. Now what we want to do is relate this distance L to the wavelength. And the way we're going to do this is imagine that there is a mirror located right there. So if there was a mirror and you were looking into the mirror, can you imagine that we could take this dotted line here and make a mirror of it over here? And so L would be, again, the distance from there to there. Now, can you spot the wavelength? So the wavelength would be the distance from here to where it repeats itself. And it repeats itself over here. So notice that the distance from a node to a node is going to be equal to the wavelength divided by 2. Or let's put the 2 on the other side. So we could say that 2 times the distance from a node to a node is equal to the wavelength. So the distance from a node to a node is from here to here. 2 times that distance is from here over to here, and then that is the wavelength. So it's a very simple formula that's going to relate the distance from a node to the wavelength of the wave. Now it can be shown, and don't you just hate it when math people tell you that? It can be shown that the distance from a node to an antinode is equal to the wavelength divided by 4. I will let you do that. All you got to do is divide this thing up into 4 sections and then put in the antinodes. Trust me, it works. So the distance from a node to an antinode is 1/4 of a wavelength. Who cares? All right, now that we've got that, how could we use this in order to predict the frequency of a noise that's going to be generated? All right, so here is a sample question. What is the wavelength of the wave pictured? So what do we know? You notice it's got 3 standing waves in it, and you notice that the distance from one side to the other side is 2 meters. And so now what we want to know is the distance from the first node. So again, let's say that this is what we're talking about. Here we got a node, and then we've got a node over here, and it's got 3 standing waves in it, like this. So if the total distance is going to be 2 meters from here over to here, we need to know the distance from a node to a node. So we got a node, and then a node is here. Well, this is 1/3 the distance from here over to here. So we need to take 1/3 of 2 meters, which is going to be 0.67 meters. So the distance from a node to a node is going to be 0.67 meters, but it's also equal to the wavelength divided by 2. So solve that for lambda, and you get 1.34 meters. Okay, now who cares? Well, now we can take that and turn it into a frequency, because the speed of any wave is going to be equal to its wavelength times its frequency. So that if it's sound and you're hearing it, you know what the speed of sound is. It's like 340 meters per second. So you know the V and you know the wavelength. You just calculated the wavelength was 1.34 meters. So now you can take those two numbers, put it into this, and solve it for the frequency, and then that's going to be the frequency of the sound that your ear is going to hear. All right, so let's take a break, and when we come back, we're going to talk about what is music.